Okay, so today I want to address a topic that's kind of technical. I want to show you the, if you like, rigorous, or some of the rigorous and formal mathematics behind what is a limit. Okay, so, behind what is an integral. And it involves limits. Okay, so when you learned what a derivative was, you learned that the formal mathematical way to define it was using limits. So the definition looked like one of these two definitions here. Let's roll this up a bit. There you go. Okay. So you could use. So I'm using delta x. Typically, the definition is written with h, but I like remembering that h really represents delta x. So either one of these methods. Okay. So we can also use limits to rigorously define, to formally define what is an integral. So the basic idea is something we've talked about before. So the basic idea is this. That if you have a function, you think of, you think of multiplying that by delta x, and then taking all those and adding them all up, and then that winds up being big F of x minus big F of a. Now, we initially talked about, so actually here, this is big F prime, so if you, or little f is big F prime, so if you like, you could think of it like this. So we thought about talking about multiplying f prime times delta x, adding that all up, and that winds up giving you big F of x minus big F of a. Okay. And that was just, and this is an approximation, and then we said, well, if you make it exact, you're talking about the fundamental theorem of calculus. Okay. And then to make it an exact equality, we use a limit. And we do that by saying, taking the delta x smaller and smaller, in fact, the limit as delta x goes to 0. So the limit is what makes that approximation into an equality. So we talked about that in approximate terms before, and in approximate terms it looks like this. Right, so instead of writing limit blah blah blah, we just say this thing is called an integral. And we use that little squiggle. So the limit as delta x goes to 0 of the sum of f of xi times delta x is simply the integral of f of x dx. So this is the formal definition using limits. So for example, we can do something like this. Here's a limit expression, but we can rewrite this as an integral. So what integral is this? So let's say the whole thing.
And the integral of,
so it's the integral
of x
squared dx. Okay. So the limit as delta x goes to 0 of the sum of xi squared times delta x. You can almost just see the symbols pass from one thing to another. The sum becomes an integral, xi squared is just the function x squared, and delta x in the limit becomes dx. So this is relatively straightforward to do it in this way. Okay. And we talked about what xi means. We have x1, x2, x3, and they're all spaced delta x apart. Okay. So this one, once again, what integral is this? It's the integral of sine x dx. Okay. We can also think about going the other way. Here we've got an integral. Let's rewrite this as a limit. So what's this going to be? The limit, right, as delta x goes to 0. Sum e to the xi times delta x. Exactly. Okay. So just doing that one step, it's almost just a notational step. But today, and I think this kind of represents stuff that we've more or less done before. So what we're going to do today is actually dig a little deeper. We're going to say, okay, we said delta x becomes dx, blah, 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 but what actually is delta x? And when we write I and xi, what does that actually mean? So today we're going to be a little more precise. So let's take a look. So first, let's start with a calculation that we've done before, which is for a given function, let's make the approximation using L6. So here's the function, f of x equals x squared plus x for x from 1 to 4, and let's make the approximation L6. Okay. So how do we do that? That looks like this. So remember, it's f of x times delta x, so, or f of xi. So what are the xi values? Well, since x is, so first of all, what's delta x? Yeah, so where does delta x, so delta x is 0.5, and then we've got f of each of our xi values. So the x is going from 1 to 4, so we start at 1, and we go 1, 1.5, 2, 2.5, 3, 3.5. So and those are the 6 things that we have to add together to get our L6. Okay. Now, where do each of those numbers actually come from? So where do we actually get delta x is 0.5? How do you find that? 4 minus 1 divided by 6. Good. Next. So we got f of 1. So where did that 1 come from? Oh yeah, exactly. It's the initial value. So the initial value, the initial x value, I'm going to call that x0. Okay. Then where did the 1.5 come from? Right. And how do you get the next one? It's that plus delta x. Okay. So x1 is going to be the initial x value plus delta x. Next one is 2. So where does that come from? Right. So I've got this plus another delta x. Okay. Now what about 2.5? Same thing again. So this is now x3. So we're going to think of this as the previous x value plus delta x, or the initial x value plus what?
Plus x. No, plus the delta x. No.
Okay. Well, the initial x value was 1. So how did we get up to 2.5?
Delta x.
Oh, why are you adding delta x? Aren't you supposed to multiply it?
We're trying to find, in this case, we're creating the next xi value, x1, x2, x3. So how do you find the next xi value? You keep adding delta x. So at this point, we're at 2.5, which is x3. So we have to keep adding delta x. So from the initial x value, how many delta x's did we add? We added 3. So now guess for the next x value, which is 3, which is in notation x4, it's the initial x value plus 4 delta x. And then x5 will be the initial x value plus 5 delta x. Okay. So we can now turn this into a general sort of formula for what we're actually doing in L6. And we're going to, in fact, turn into a general formula for what we do when we have Ln. Okay. So what is delta x? In the case of we're finding Ln for the function f of x when x is between a and b. B minus a over n, that's going to be your delta x. Next, what is your delta, what is your xi? Okay. So it's going to be the initial value, which is x0, or we could actually just write that as a plus what? Okay, so there is going to be a delta x there. I times delta x, exactly. So that the ith x value, you've added I delta x's, exactly. Okay. Now also, all our xi values, I starts at what number and goes to what number?
I start from 1 to 5.
The boundary is like the beginning interval from A to B.
So remember, I is the index. That's actually where I comes from. It stands for index. I is the index that counts where we are. So the way that I wrote this out, where did I start at? Yeah. And what was the last I value? Okay. So in my example, in this example, what was the actual in L6? What was the last I value? It was 5. So for n, what do you think is going to be the last I value? N minus 1. Okay. So notice that this, in fact, now normally you'd say if we want to have, if you think of it in terms of rectangles, Ln, if you want n rectangles, you'd number them 1 to n. So we're actually numbering them, for technical reasons, we're numbering them from 0 to n minus 1. But that still gives you n things. Okay. So now let's use these expressions to actually construct Ln. Let's see. So we know that Ln is going to be a sum of, well, let me see. Actually, oh yeah. Here. So we've said previously that Ln is just the sum of f of xi times delta x. But now we're going to add in some more stuff. So we know, I already filled it in, we already know that the sum of that I, when you're taking the sum, goes from 0 to n minus 1. That's the first thing. Second of all, what is xi? Well, we now know what the sort of more rigorous formula for xi is. And we also know what the formula for delta x is. So now the formula for Ln looks like this.
I is going to be start 0.
So that's a good question. But so first, does everyone see how I just replaced each thing with what we know, with its sort of its new, more detail-oriented formula? Okay. So now this comment about I. So the way that it's set up here, I goes from 0 to n minus 1. Now, we constructed this using Ln, which if you remember what this means we're using left endpoints in order to find what the value is. So for example, for the rectangle that goes from 1 to 1.5, we're using f of 1 to say what the height is. And that's on the left side. Now, alternately, you could use the function value at 1.5. You're using the right side of the rectangle. So we didn't go into the details of this, but that's on the right side, so that's called Rn. And then you'd start with x1, and then your I would go from 1 to n. So that's a technical detail. We're not going to worry about this. We're going to stick with Ln, which is using left endpoints, which is what we've done the whole semester. Okay. So there are options to answer your question that we're not going to worry about it. So we're going to just go through with it this way. Okay. And again, these are technical details, and I want to go through as few technical details as possible while still capturing the idea that we're doing something very rigorous. Okay. So now let's use this in an example. Okay. So let's take the integral from 2 to 3 of x cubed dx, and let's do 3 things. First of all, just write this as an approximation using L5. Then as an approximation using Ln. And then take the limit to make it an expression for the exact value of the integral. All right. So L5, let's see. Okay. So how would we do this? So once again, we need to figure out What's delta x? What's our a? Et cetera, et cetera. So in this situation, in part A, what is delta x going to be? 3 minus 2 over 5. So that's 1/5 or 0.2. Okay? And what else do we need? Let's see. So we're also going to need a. So what's a? A is 2. Remember, we're using our convention. The boundaries of integration are a and b. Okay. So if you stick that all in, what do you get? It looks like this. Oop. And that should be the sum from 1 to 4. Because it's L5. So this would be in summation notation, how to write down L5. I think we've had more experience just writing it down term by term. This is how you would write it down compactly in summation notation. So notice that here's your A plus I times delta x, and that's your xi value, and then you're applying the function to it, which is that whole thing cubed, and then you multiply f of xi times delta x.
And how did you get the 4 in the boundaries?
It's 5 minus 1.
The sum goes from 0 to n minus 1. And in this case, n is actually 5, so it's just 4.
I have a question. Oh, it's, okay. 2 times, okay.
Okay. So that's what you do when you have L5. What about Ln in general? So Ln in general, get this. Okay. So what's changed now? We're taking the sum as I goes from 0 now up to n minus 1. And then the xi value is, once again, it's a plus I times delta x. But what's delta x? It's 3 minus 2 over n. So it's 1 over n.
Isn't it supposed to be 2 minus I? Doesn't it change to that?
It's b minus a over n, so it is 3 minus 2, because we want to know the length of the length of the interval. Yeah.
Does not change the boundary now? Because it's going to be from.
And so then the answer to part C is very simple. You just take that expression and just slap limit in front of it. Now in this case, we're going to take the limit as what? The limit as n goes to infinity. Okay. So to connect it with what we've talked about before, as n goes to infinity, what happens to delta x? Delta x, since delta x is 1 over n, as n goes to infinity, delta x goes to 0. So notice that those two ideas in terms of limits are actually basically equivalent. Saying delta x going to 0, saying n goes to infinity means basically the same thing. It's just a question of notation and how we choose to write it down. Okay. So now we're going to talk about calculating these things. We know how to calculate this because there's just 5 terms. So we can write out 5 terms, cube whatever we get, and then just add them up. So we've calculated things like L5 before. Turns out we can also calculate it when there are n terms. And then we can also take the limit of that expression. And that's what I'm going to show you right now. Okay. So here's the expression for ln. And so I'm just going to do some algebraic manipulation. So first of all, I've got something cubed, so I'm actually going to multiply it out. So when you actually cube it and multiply it out, you get this. Okay? Next. Now I've got the 1 over n on the outside. I'm going to distribute that. So you get this. So now I'm going to do some work with sums. So first, I'm just going to separate this into 4 different sums. So because I want to be able to think of each of them individually. And the next thing I'm going to do is something for which you have to understand summation notation. I'm going to pull out a common factor from each sum. So think about what a sum means. I know we haven't worked much with summation notation, but think about what a sum means. It means that you're adding up a bunch of factors. So if you're adding up a bunch of things, if they all have something in common, you can pull that out. So what does, for example, let's take the sum over I of 3i. What will every single term have in it? It will have an I, but the I is changing. Because in the first term I is 1, in the second term I is 2, and the third term I is 3. So I is not going to be the same thing in each term. But what is going to be the same thing in each term? The 3 is in each term. So we can pull out the 3.
So we can pull out all of those numbers?
So we can pull out everything that's the same in each term, which is anything that does not have an I in it. Because I is changing, but the other things are the same in every single term. Okay. So that's probably the most technical and abstract thing I'm going to say today. So once that happens, here are the 4 separate terms, 4 separate sums with the common factor pulled out on the outside. And so what's left is, notice when you factor out an 8n, what's left is it nothing? There was like a 1 there. So there's a 1 left. And from the second one, when you factor out the 12 over n squared, what's left is I. In the next one, what's left is I squared. And in the last one, what's left is I cubed. So basically, we have to know what that sum is. So to evaluate this, we need some special sum formulas, and those special sum formulas are given to you right here. And there's actually so notice that this is the sum of I raised to some power in each case. There's a formula exists for every single one of these. So we're gonna just work with the sum for all these different formulas up through I cubed. So these 4. So now we can just replace each summation expression with this other expression, which is in terms of n. And so let me say, we could talk about where these formulas come from, and I'm just going to skip that part. We'll just take the formulas as given. Okay. So when you replace them, you get this. 8 over n times n minus 1. And then the next one is 12 over n squared times n times n minus 1 over 2, et cetera, with the summation of I expression replaced. So now I'm going to multiply it out and see what each term is. So when you do that, you wind up with these 4 fractions. So that's ln. And this is the best thing that, so ln says if you tell me how many rectangles you break it up into, I can tell you what that area approximation is going to be. But that's still an approximation. So we've answered part B. How do we find the approximation? But now we're going to go on to part C. Make this exact by taking the limit. So the integral is actually equal to the limit as n goes to infinity of this expression. So now we just need to evaluate this limit. As limits go, this one's actually really, really easy. because since n is going to infinity, and all you have are a bunch of fractions of rational expressions with polynomials on top and bottom, all you have to do is compare lead coefficients.
They'll go to infinity.
So,
This whole thing goes to
No,
because
so this is very brief. This is a brief revisiting of how do you calculate a limit. So in the first fraction, what's that going to be in the limit? Just a quick reminder, since n is going to infinity,
or 1.
it's as if negative 8 isn't even there because it's so insignificant. 8n over n is going to be 8.
Wait, what?
And in the next one, with n going to infinity, sure, 6n is going to infinity, but 6n squared is much, much bigger and it dominates. So it's as if everything aside from the n squareds are not there. 6n squared over n squared will give you 6. Again, that's the informal version. You could do this formally, but I just want to get you quickly through the details of saying what the limit is. And so this will just give us 8 plus 6 plus 2 plus 1 over 4. And that works out to 16.25. So what we've actually done is we've taken the integral, written it as a sum, which is an approximation. Then we said we can make that approximation exact by taking the limit. And it was a long way to get there. My question is this answer what we think it should be? Well, we have another way to find integrals, don't we? We can just do the integral. So let's check it. So the integral from 2 to 3 of x cubed dx is just x to the 4th over 4 evaluated from 2 to 3, which is, if you plug it in, 81 over 4 minus 16 over 4, which gives you 16.25.
What's the point?
So it's a reasonable question to ask, what's the point of doing all that business? So the point of doing all that business is, this is formally what has to be done if you want to prove it. Now, for the most part, certainly in the context of this class, we're usually, well, let me put it this way. How concerned you are with proving things is up to you. If you say, oh, the proof is really fascinating, and all those details are great, I want to be absolutely mathematically certain that this actually works, then all the details that we've just done here are very appealing. If you just say, I trust that somebody else proved it and I just want to apply this to problems, then this is less interesting to you.
But could you possibly have a question like that?
Okay. So now that we've sort of seen the whole journey, let's go through another problem. So let's find this integral. Once again, A, by setting up the sum and taking the limit, and then B, using integration, which obviously will be much easier and quicker. Okay. So first, setting up the sum and taking the limit. So ln equals this concoction. So where does this come from? Let's try to set it up together. So what do we need in order to set up the sum?
We need delta x.
Yes, we need delta x. So what is delta x going to be?
That's going to be 3 over n.
So delta x is going to be, right, 7 minus 4, which is 3 over n. Excellent. What else do we need? We need xi.
Right.
So what is xi going to be?
It's going to be 2 times 3 over n. Right?
So any xi is going to be the initial value, which is what? 4. Plus what?
2. Over n.
Plus I times delta x, where delta x was 3 over n. Okay. So now that we know those things, we can say the sum is simply f of xi. And what is f of xi? It's 2 times that minus 1. So there you go. 2 times that thing, 4 plus I times 3 over n, minus 1. And then the whole thing times delta x, which is 3 over n. So that's the individual term, and then you say, okay, we need to sum that as I goes from 0 to n minus 1. And that's ln. So now that we have the expression for ln, we can actually go about the same procedure we just did and expand it and get it to be just in terms of n by using those formulas. So let's expand it. So if you expand it, if you simplify inside and then if you simplify inside, you get 7 plus 6i over n. That's just algebra. And then if you multiply by 3 over n, that gives you 21 over n plus 18i over n squared. Again, just algebra.
Isn't it just easy to take the first three n out and then just deal with the 7 plus 6i?
So at this point, we know that we're going to have 2 separate sums, and each one needs to be replaced. So the first sum is just going to be the sum of, well, there's no I there, it's just going to be the sum of 1. And we know that that's n minus 1. And then the next one, we need the sum over I, and the sum over I is n times n minus 1 over 2. So we substitute that in, and we get this. 21 over n times n minus 1, 18 over n squared times n times n minus 1 over 2. Straighten it out with some more algebra, and you get this. And that's ln. So this is now an approximation of the integral. Now to get it exactly, take the limit as n goes to infinity. Of ln, which is limit as n goes to infinity, of that expression, which is just going to be, the first one is,
30.
so the first fraction is going to give you 21. The second fraction will give you 18 over 2, which is 9. So it's 30. So that's this if you use the sum, and then if you find ln, then take the limit of it. Or just take the integral. So the integral of 2x minus 1 is just x squared minus x, evaluated from 4 to 7. 7 squared minus 7 minus 4 squared minus 4 gives you 30. So now I'm going to ask you a different kind of question. Here is a limit of a sum. Calculate that.
Okay.
How do you do this?
Distribute the 5 first.
Okay. So you'd say we've got something to the 5th, so you actually have to multiply that out. Remember, this to the 5th is not 1 to the 5th plus the other thing to the 5th. You've got to basically FOIL it out 5 times. Okay, so do that, and then you've got your sums in terms of i's. You're going to have a sum of I, some I squared, some I cubed, all those things. And we know how to do that, and that's like there's a procedure to work all those things out. There's another slick way to do this.
Change it to an integral.
Change it to an integral. Exactly. Because we know that in all these problems, the short way is if we can just make it an integral, we know how to do integrals. So what is this as an integral? We've got to figure that out.
So it's an integral from 1 to.
Okay. So you've answered the first question. It's an integral from something, from a to b of some function. So all we need to know is those 3 things. So the a value is the easiest thing to identify because a is right there. And what's the b value?
4.
Why is it 4?
Because it's b minus a.
Yeah.
4 minus 1.
Because b minus a is 3, so b has to be 4. Very nice. And now, what's the function?
The function is, I think it's x to the 5th.
Yeah. And how do we see that? Because here's the expression for xi, and what are you doing to it? you're raising it to the fifth power. So the function is just x to the fifth. So this whole limit just equals the integral from 1 to 4 of x to the fifth dx, and that, of course, is a trivial integral for us. X to the 6 over 6 from 1 to 4 is that, which works out to 682.5.
This is in the notes. You're gonna post it.
So in particular, to do this kind of problem, what do you need to do? You need to take the limit of the sum, and you need to find three things. What do you need to find? You need to find a and b, and what's the function. And once you know that, you know what the integral is, and then it's easy. So there's a take-home lesson from this last kind of problem, which kind of applies to, in a sense, this entire course. The tools of calculus are very powerful, and they make a problem that would otherwise be very long and tedious, as we saw previously, into something that you can do very quickly and very easily.